Waves are a fundamental concept in both mathematics and physics. They can be found in various forms, from the ripples on a pond to the electromagnetic waves that transmit signals through the air. One of the most interesting aspects of waves is that they can add up to produce arbitrary periodic functions, such as sound waves. Qualitatively, this can be explained through the concepts of sines and cosines and Fourier series. Sines and cosines are two basic trigonometric functions that are used to represent periodic phenomena. When graphed, they produce a wave-like pattern with a repeating cycle. The key to understanding how they add up to produce arbitrary periodic functions lies in their relationship to each other. Sines and cosines are actually two sides of the same coin, known as the sine and cosine waves. This means that for every value of x, the sine of x will be equal to the cosine of x plus pi divided by 2. Therefore, their sum or difference will always result in a straight line. This relationship between sines and cosines is what makes it possible for them to add up and produce any periodic function, as they can cancel out each other's fluctuations. The concept of Fourier components further explains how sines and cosines can add up to produce arbitrary periodic functions. Each Fourier component corresponds to a sinusoidal wave with a different wavelength or period. This means that by adding together different combinations of sines and cosines with varying wavelengths, we can create any type of periodic function. This is known as a Fourier series, and it is a powerful mathematical tool used to analyze and understand complex wave phenomena. Sounds, for example, are essentially waves of vibration that travel through a medium, such as air or water. When these vibrations are graphed, they can be represented as a series of sinusoidal waves with different frequencies and amplitudes. This is why instruments such as the guitar or piano can produce different notes, and they are essentially creating different combination of sinusoidal waves. Finally, it is important to note the difference between waves in space and waves in time. While both types of waves exhibit properties such as amplitude, frequency, and wavelength, their behavior and characteristics differ. Waves in space, such as light and sound waves, travel through a physical medium and require a source to propagate. On the other hand, waves in time, such as the ticking of a clock, do not require a medium and can occur independently. In conclusion, sines and cosines play a crucial role in understanding how waves can add up to produce arbitrary periodic functions. With the help of Fourier components, we can break down complex waves into simpler sinusoidal components, making it easier to analyze and understand their characteristics. This concept not only applies to sound waves, but also to other types of waves in nature.